In the last video, I explained different power electronic circuit topologies used to build EV chargers. In today's presentation, I will demonstrate how to simulate an EV charger using Matlab. So let's get started. I had explained different topologies for both AC-DC stage and the DC-DC stage. Now I am simulating a single-phase EV charger. For that I am using an interleaved boost converter for the AC-DC section and phase-shifted full-bridge converter for the DC-DC section. Now we open the Matlab and start doing the simulation. Add an AC voltage source. Set the peak voltage 325 and frequency 50 Hz. Add a voltage measurement block. Connect it across the AC voltage. Add a go-to block. And connect it to the measurement block. Name it as VAC. Add a current measurement block. Add a go-to block. And connect it to the measurement block. Name it as IAC. Add a diode. Form the single-phase bridge using diode. Add a voltage measurement block. And connect to the output of the diode bridge. Add a go-to block. And connect it to the measurement block. Name it as VIN. Add a series RLC branch. Set the branch type inductance, and value 10 mH. And connect to the output of the diode bridge. Add a current measurement block. And connect to each inductor. Add a go-to block. And connect it to the measurement block. Name it as IL1. And name it as IL2. Add a MOSFET. And connect to each inductor. Add a from block. And connect it to the MOSFET. Name it as PWM1. Name it as PWM2. Add a diode. and connect to each inductor. Add a series RLC branch. And connect it to each diode. Set branch type RC, the value of resistance 0.02, value of capacitance 5600 microfarad. Add a voltage measurement block. And connect it across the RC branch. Add a go-to block. Name it as Vout. Add a MOSFET. Form the H bridge using MOSFET. Add a from block. And connect it to the MOSFET. Name it as PWM3. Name it as PWM4. Name it as PWM5. Name it as PWM6. Add a linear transformer. And connect to the MOSFET bridge. Set the transformer parameters as you see on the screen. Add a diode. And form the secondary diode bridge. Add a series RLC branch. And connect to the diode bridge. Set the branch type L, and value 150 microhenry. Copy the RLC branch. Set branch type RC, resistance 0.02, capacitance 600 microfarad. Add a current measurement block. Add a go-to block. And connect it to the measurement block. Name it as IBAT1. Add a battery. Flip the battery block and connect to the output. Set the battery type lead acid. Nominal voltage 48, rated capacity 150 Ah, initial SOC 50%, response time 1 second. Add a bus selector. Add battery voltage to the bus. Add a go-to block. Name it as VBAT. Now I will connect the controller blocks. Copy the input voltage signal. Add a RMS block. Set frequency 50, and initial RMS value 230. Add a product block. Add a constant block. Set the value square root 2. Copy the product block. Change the number of inputs. Copy the product block. Connect V into the product block. Add a constant block. Set value 400. Add a sum block. Change its sign to plus minus. Connect V out to the sum block. Add APID controller. Set the value of KP 0.25 and KI 30. Copy the product block. Add a sum block. Change its sign to plus minus. Copy the sum block. Connect inductor current to sum block. Add a transfer function block to implement the PR controller. Set the numerator and denominator coefficients for the PR controller. Add a relational operator. Change the operation to greater than or equal to. Add a repeating sequence. Set the values for 0 to 1, 5 kHz triangular carrier waveform. Connect the PWM signals to the output of the controller. Add a constant block. Set the value 55. Add a sum block. Change its sign to plus minus. Connect the battery voltage to the sum block. Add API controller. Set the value of KP25 and KI5. Also limit the output between 0 and 180 degrees. Add a saturation block. Limit the value between 0 and 37.5. Here 37.5 is the maximum battery current. Copy the sum block. Connect the battery current to the sum block. Copy the PID controller. Add a Matlab function block. Write the code to generate the phase-shifted PWMs for the converter. Connect the function block to PI controller. Add a constant block. Set the value 50,000, which is the switching frequency of the converter. Add a clock. Set decimation 1. Add a logical operator. Set the operation not. Connect the PWM signals to the logical operator. Add a scope. Connect input voltage and current to the scope. Add another scope. Connect bus voltage to the scope. Add a display. Connect battery voltage and current to the display. Open the model settings. Choose fixed step solver type. Set step size 1e rise to -6. Add a power guide block. Set simulation type discrete and sampling time 1e rise to -6. Here I made a mistake in the connection, so just correcting it. Set simulation time 1.5 seconds, and run the simulation. Here you will see the battery voltage and current. The battery voltage is increasing as we keep charging the battery. This is the bulk voltage at the output of boost converter, and which is regulated at 400 volts. This is the input voltage and current. Current is sinusoidal and is aligned in phase with the voltage. So the power factor is unity and the PFC circuit is working fine.